Okay, I think we can get started on the final session of the UV Meets the IR virtual conference here at KITP. So first, we have Sergei Dubovsky here from NYU to tell us about UV Meets the IR on the string worldsheet. Sergei?
Okay, thanks a lot for the invitation to speak here. And I should say, when I received the email from the organizers inviting me to speak, my first reaction was that I really liked the conference. I liked the list of speakers, but I thought that, well, for a number of years, I was thinking about different stuff, mostly on confining strings. So I should say just no and maybe attend the talks. But it was very tempting because I really liked the lineup of speakers. So I didn't respond immediately, so I was kind of postponing for a few days, trying to find an excuse. And then I did find an excuse, and I already opened email to say that, no, I'm not going to speak. Sorry, guys. But then it occurred to me, if I just skip the second, like this workshop has very long title, if I drop the second part of the title, then it actually perfectly fits in what I'm doing. And so I decided, okay, I'm going to give this talk. So you see my title, and oops, why? Sorry, I'm not for some reason. Okay, so, and I should say, so this talk will be mostly a review of well-known facts and kind of things I'm thinking about, and some share some personal questions, confusions, hallucinations. So I apologize, I won't provide any references, but I still want to thank people who are working with me about related topics over the number of years. So I listed them here. Well, let me start with the following question. So this workshop is about meeting between UV and IR. So the question is, where do they meet? And I think possible answer is provided by the full expanded title of the workshop, that exploring the effective field theory bounds, which kind of suggests, I think, the meeting, that this meeting of the two happens in the IR. So we don't have direct access to the UV, but it descends down to UR and establishes the rules which govern some of the low energy coefficients and some other pieces of physics. And I think that's a very interesting set of explorations, and that was mostly the topic of previous talks. But I think one may try to be more adventurous and ask, can it be another way around? Can somehow one start from IR, and that may govern the whole physics in the UV? And for those of you who don't read Russian, so this picture here, it's probably from 1920s. It's like a piece of Soviet propaganda, atheist Soviet propaganda. It says, the fight against religion is the fight for socialism. But I don't necessarily subscribe to any of these pieces of art, what it says here, but I think it kind of illustrates the point I'm trying to make. And given there were many talks along the first line of thinking, so I will, for a while, most of the talk will be trying to pursue this second direction. And just to make things more concrete, so in QFT, that sounds, this idea sounds a bit crazy because the way we used to set up things in QFT, so that we define microscopic degrees of freedom, there are fundamental interactions in the UV, and trying to derive the rest going from there. However, presence of gravity changes this. This is kind of well appreciated. We don't need a Planck scale collider to deduce what happens in transplanckian collisions. We know the answer. So we collide particles at transplanckian energies that black holes are being formed, and then they evaporate. Oops, sorry. So and actually, the very same process precludes one from defining local observables, because if you're trying to do something locally in the lab with arbitrary precision, then your kind of clocks and rods becomes too heavy, and your lab will collapse into a black hole. So that makes notion of sub-Planckian microscopic degrees of freedom moot. So kind of in gravity, we know that like semi-classical IR physics determines also to a large extent determines what happens in the UV. And well, up until recently, my own view on that was that it's all true, but still somehow we know, for instance, with doing semi-classical calculation, we conclude that black hole evaporation is not unitary. So clearly some big pieces of physics are missing. And remarkably, as we are learning in recent years, that actually also semi-classical gravitational path integral is smart enough even to tell us that Hawking evaporation is a unitary process. So I think that on its own kind of is a motivation for me, at least, to pursue this line of thought more seriously. And to be more concrete, I'll go through very specific examples where actually this thinking leads to it is quite successful, and it should illustrate that this thinking is more than just visual thinking. And the simplest toy model which illustrates this, how one can deduce the whole physics starting just from kind of one IR, classical IR principle, is the following one. So we can start with a theory of a single long free critical string. It can be superstring, it doesn't really matter, the story is the same, but for simplicity, I'll focus on a just bosonic string. And well, classically, this system is described by Nambu-Goto action. And while this Nambu-Goto action describes an integrable classical system, and well, all what you can do when you have infinitely long string, what you can do, you can introduce oscillations on the string, and they will propagate along the string and collide with each other. So, and classically, if one solves this classical Nambu-Goto equation, one sees that first of all the scattering is integrable. So this oscillations, they go through each other, bumps on the string go through each other, and asymptotically don't change their form. But there is a time delay proportional to the energy, which is simply the statement that when you excite the string, then its proper length gets larger proportionally to the energy, and that's what causes this time delay. So this is what happens classically. And now what one can do, one can enforce this classical kind of, which more or less in this context, just like in the context of gravitational theory, classical is almost the same as IR. So classical geometrical principle, one may try to enforce it as an exact quantum statement. And then one would write the following phase shift. So this is here, LS is a string width and S is Mandelstam S. So that's just a phase shift corresponding to what I said on the previous slide. So the phase shift which gives rise to time delay proportional to the energy. And this turns out to be, so the phase shift gives exact correct worldsheet S matrix of a critical string. So kind of this is an example where kind of this strategy of starting from some classical principle and pushing it all the way just immediately gives rise to the full answer for what happens in the quantum theory. And actually this theory describes an integrable model of 2D gravity with string lengths playing the role of Planck lengths. For instance, in the sense that locality lost at distances below that scale because of exponential behavior of this S matrix as a function of S at high energies. Okay, so of course this is very nice, but maybe isolated example. Actually, there is a larger set of examples which generalize this. So one can generalize this whole story for general two-dimensional QFT. So it was called gravitational dressing of a general two-dimensional QFT. So one starts, what one can do, one can start with general quantum field theory and then consider general scattering process. And so if here Sn is my S matrix of my initial QFT, one can write mu S matrix, which is multiplied by this phase shift here. And so here P is on-shell momenta of incoming and outgoing particles. And this new S matrix defines a consistent two-dimensional theory. So, well, let's generalize the previous story first in the sense that, well, if I start with free boson, that's exactly the situation which I was discussed before. Free massless boson, that's a theory on the worldsheet of a string. And also that kind of the construction of the full theory goes that one starts with some IR piece of physics, which is this initial QFT, and then one introduces a relevant parameter in this theory, some UV scale, by multiplying by this phase. It's not completely clear, kind of in this formulation, it's not completely clear what is the underlying principle for writing this formula. And actually, this whole construction, the reason I think one reason it's interesting, it challenges the hierarchy problem because it shows that it's possible to introduce UV scale into theory without distorting the mass spectrum, without kind of, because this UV scale.
Okay, I'm sorry to interrupt, but for example, in terms of dispersion relation, only one of those S or S hat would be the one which would be okay in terms of this exponential behavior, right? So for one it would be dispersion relation, for another would be no normal dispersion relation, right?
No, that's not quite true because yes, so I mentioned also the previous. So this phase shift here, it's kind of it's borderline violating locality. So if LS squared is positive, it's true there is an exponential behavior at large S, indicating that the theory is somewhat non-local. But on the physical sheet, nevertheless, the amplitude is bounded. Polynomial, it's exponentially small. So if there is essential singularity doesn't still allow to write a dispersion relation.
I understand that it shows up on the other sheets, you mean, right?
Right, yeah. And that's the reason why this theory is gravitational. So this theory doesn't allow, indeed, this theory doesn't have local operators, but on the other hand, that's in theory of gravity, I also don't expect to find local operators. So as I said, there's challenges, for me at least, the challenges the of hierarchy problem, because here I managed to introduce UV parameter in the theory without distorting any hierarchies. Well, and actually there are other views at the same in the same model. So the same dressing was reformulated as what's known under the name of TT bar deformation. That's it's kind of operatorial definition of the same theory. So the way one defines this is the following. So you think about space of all effective field theories. You start with your IR theory, which is this star here, and then you think about local operators as tangent vectors to the space of field theories, simply because, well, tangent vectors is something which shows you which direction to go, how to deform your theory. And that's, if you have an action, you add to your theory this operator with small coefficient. So it's natural to think about local operators as tangent vectors to space of field theories. And then one defines a trajectory the following way. So one defines a trajectory in the theory space as a trajectory which at each point it's tangent to a particular operator, which is present in any relativistic two-dimensional theory, quantum field theory. This is what's called TT bar operator, but really it's the expression which is written here. But this is determinant of T operator. And so these series, which I defined in the previous slide by S matrix, they correspond just different points along this trajectory. And for instance, if I started in the with the CFT, that would be, this trajectory would really be RG trajectory. In general, it's not RG trajectory, but it's just some trajectory in series space. Especially in the example when it's RG trajectory, so it clearly illustrates kind of the point which we are starting. So it's a new way, and I think it sheds light on why this theory, this construction avoids hierarchy problem, because the way we build theory here is that we start from IR seed, and then we shoot trajectory in the UV, as opposed to what we are doing normally when we start from UV fixed point and we shoot trajectory in the IR. And this IR seed theory fully determines the UV. Again, it's not 100% clear, I think, yet kind of what is the underlying principle, why this trajectory exists. It relies on some remarkable properties of this operator, which were discovered by Zmalochikov. But still, I think it sheds some light on what's going on here. Well, finally, I should say this gravitational dressing is it indeed describes the theory of gravity, it turns out. So this is the path integral formulation of this theory. So what's written here is the partition expression for the partition function of the full model. So this Z0 is the partition function of original quantum field theory in some background metric J alpha beta, and then one integrates averages over metrics with the weight written here. So E here is a two-dimensional version of Weirbind field. It's so G alpha beta is the square of E. So it's a very simple theory of gravity. It's kind of loosely speaking, one may call it flat space JT gravity. Essentially, what one does, one integrates over all. Like this term here is ensures that the metric remains flat. So this path integral is integrated over different kind of gauge non-equivalent classes of flat metrics. And so the role of gravity here, the only role of gravity here is to introduce this kind of Stuckelberg fields which appear here, this axis, which one may think about them either they're similar to target space coordinates for a string, or one may think about them again, relational observables, dynamical clocks and rods of this theory. And the way this dressing works is that you insist on using these target space coordinates and your physical coordinates instead of worldsheet coordinates. And that's how this S matrix arises. So kind of the whole, so this UV scattering, which is encapsulated by this phase sheet, we see that it arises not because there are some new UV degrees of freedom, but because you stretch your dynamically stretch your space-time without introducing new degrees of freedom in the UV. So there are no new degrees of freedom in the UV. And so again, I think it illustrates this point, so that somehow here all the non-trivial content of the theory is really present in the IR, and then UV is built from there following some principle. Well, as a curiosity, so this parameter lambda here is related to what I was calling LS squared in the previous slide. It's -1 over LS squared. Actually, as one looks about this, the theory of gravity, that it corresponds to vacuum energy, but it plays like peculiarity of two-dimensional gravity that plays more of lot of Planck mass rather than vacuum energy. But still, if I take positive lambda theory, so that theory would correspond to this phase shift with negative sign, which would correspond to time advance. So that wouldn't allow actual even dispersion relation, as Arkady pointed out. And that's an example of UV completion of the wrong sign superluminal theory. So which illustrates the point when we talk some things about which are kind of excluded in the IR, really there is always some underlying assumption about UV. So here, in particular, preferring one sign with respect to other corresponds to kind of preferring amplitudes which have essential singularity on the infinity, but still allow to write dispersion relation with respect to amplitudes which don't allow to write dispersion relation. Okay, so this is all nice, but of course, kind of the natural question is, so is it like just singular class of examples, or there are more theories with similar UV behavior, but hopefully with more interesting dynamics? And well, the answer is yes. And we know that there is a large class of physically interesting and poorly understood theories, but which we have to understand for other reasons, as I will explain now. And so basically all what one needs to do to construct them is to replace, like I started with a critical string in my discussion, but one can replace that critical string with a confining one. So more specifically, so now let's consider confining QCD-like theory with a joint matter, so that there is an unbroken center symmetry there, and pure glue is the main example. And let's take the strict planar limit, strict top limit. So in this top limit, like the bulk theory becomes free, but it's still confining. So one can consider now dynamics of a single confining string. And just like before, I was considering scattering on the worldsheet of a critical string. Now I can consider scattering on the worldsheet of confining string. And this scattering at low energies is still described by the classical Nambu-Goto action. But now the full theory is in general non-integrable. So at first sight, this example goes against what I was proposing in the beginning, because high energy dynamics here seems to be completely disconnected from what happens in the IR. For instance, we know that if one kind of thinks about UV of this theory, one should find QCT partons, so that looks very different from the dynamics of long wavelength mode governed by Nambu-Goto. However, we know, given that we know QCD, we can draw a cartoon of how high energy of worldsheet scattering in this theory will look like. Namely, kind of, if I think now about my high energy excitations as this blue, this corresponds to parton, meaning if it's pure glue, that's really gluon, which dressed by the long flux tube, that as one scatter them, they go through hard collision process, which really at very high energies means nothing because theory is asymptotically free, so not much happens during this hard collision process. And then they overshoot, they form kind of the zigzag configuration. Because I work in a strict planar limit, my string never breaks, so this zigzag will eventually turn partons and they will shoot back. So that's kind of high energy collision links in the degrees of freedom which we understand. So by the way, it's an interesting example where kind of one naturally led to integrable theory. So here, because of asymptotic freedom, one doesn't expect this hard particle production, but on the other hand, confinement enforces non-trivial phase shift. So here, dynamically, one in this UV asymptotics, one is led to non-trivial integrable theory. And interestingly, so first we find that ultimate UV asymptotics, even though it's kind of looks different from somewhat different from Nambu-Goto, it's still dominated by semi-classical stretching of space-time. And actually, this zigzag, it produces the same time delay as low energy Nambu-Goto calculation, although geometrical picture is somewhat different, but not drastically different. Kind of in the Nambu-Goto language, one says high energy excitation of string makes string longer. So here I'm thinking about high energy excitation of a string instead of as a parton insertion, but at the end, I still produce long string during scattering. So to a large extent, still the logic goes through. So somehow the principle which one finds at low energies here goes all the way to the UV. But however, the actual story appears to be more involved because this integrability here is only approximate. It's broken at intermediate energies. And actually, so to see what's in more detail what's going on, let's focus on the simplest perhaps case, namely on the pure glue theory in D equals 3. So when in this case there is a single Goldstone boson which lives on the worldsheet, so the theory on a single Goldstone mode. And let's write a dispersion relation for the corresponding 2-to-2 S matrix, which is very similar to dispersion relation, which is written to derive positivity bound. However, while it's slightly different, I'm not writing it for amplitude, but I'm writing here it for the log of S matrix, for the reason which will become momentarily clear momentarily. And this dispersion relation, well, it just says that this integral of 1 over S times logarithmic derivative of the log of the S matrix is equal to the 2 pi I sum over zeros of the which are present on the physical sheet. Now, the reason that I wanted to write it for the log of S matrix is that I'm making the following assumptions. I'm making the assumption, well, at the low energy, it's not really assumption. I know how my amplitude behaves, so it's I can Taylor expand it, and I find this UV causativity, which appears in UV coefficient, which IR coefficient, sorry, which appears in the positivity bounds. In the UV, I am assuming that it's dominated by this phase shift, which I was drawing before. And that's the reason I want to pick up the contributions. That's the reason I wrote dispersion relation for the log of S matrix. And one arrives at the following expression, namely one finds the difference between this IR and UV scales is given by this expression. So there are two terms here. One is an integral over the cut that corresponds to particle production, and another is a contribution from zeros on the physical sheet, which should be thought of as contribution from resonances. Usually we talk about resonances as poles on the physical sheet, but actually if one wants to stay on the physical sheet, then it's more appropriate to talk about them as zeros on the physical sheet. Now, naively, this dispersion relation actually in conflict with the geometrical picture which I provided you before, because what determines the high energy time delay is this, what I call LUV here. But on the other hand, so this expression on the right hand side, it's always positive or non-negative. So if it's positive, it's on zero, then it tells me that this coefficient LUV is actually different from the IR tension of a string. And on the other hand, in geometrical picture, it's IR tension of a string, which was providing the mechanism for time delay. And this is the exact picture. So it looks like there is some puzzle here. So let me give some comments on that. So first of all, actually in the absence of particle production, so if one looks at this and insists on geometrical interpretation, then that's one way to derive it to the ISS matrix. Namely, so if there is no particle production, then one says, okay, kind of if I insist that time delays given by this geometrical picture, then it should be that there are no resonances, so there are no zeros. And then the only possible function which you can write, which is exponentially bounded, is this e to the s. So it's another way to arrive to it. And indeed, there is a rather involved proof which shows that the only integrable phase shift compatible with target space Poincare symmetry is of this form. So this argument kind of provides shortcut to this proof. Actually, this presence of particle production may be compatible with the physical, low energy physical intuition if the latter is extensive long time process. And indeed, one expects of thinking about this picture. There is a long period of time here where these partons, they move with acceleration. So actually one would expect, again, from IR physics, one would expect there should be some Unruh type particle production here. And which means that the actual time delay will be given not just by string tension, but it will be shorter than that because partons, that means that partons lose their energy more efficiently by emitting soft low energy modes. So actually it looks like maybe there is no contradiction here, although I'm a little bit confused. That will tell that actual high energy process is really the dominant high energy process is not 2-2-2 scattering, but 2-2-2 plus lots of soft excitations. And I'm not sure then whether I'm looking at 2-2-2s matrix to determine what is the corresponding phase shift. So it's a little bit, I'm a little bit puzzled about that. And also this argument actually suggests I don't see similar interpretation, like long distance interpretation for resonances. So it would suggest then that there should be no resonances, which is an agreement actually for what we know about pure glue theory. In pure glue theory in D = 3, there is lattice data which strongly suggests that there are no additional degrees of freedom on the string bullshit. But more generally, I may think of adding some adjoint scalar field, for instance, with phi cube interactions and I would expect that it should be possible to produce resonances. So it's probably something is missing, but I feel that probably there is some more to learn from this dispersion relation here. So finally, let me tell you now about D = 4 case, which is probably more interesting. And here we encounter actually a very interesting and puzzling instance of UV-IR meeting. Namely, let's start from pure glue theory again. And here we can do two calculations. One calculation we're doing in the UV. So this calculation is being done with just perturbative glue dynamics. Namely, we calculate leading log violation of scale invariance in that theory. Meaning, in other words, we're calculating one loop beta function, and we find this famous answer here. Another calculation we're doing the IR. So we go on the worldsheet of a confining string, which at low energy is described by Nambu-Gotar. And in D = 4, Nambu-Gotar theory, as I said, it's classically integrable, but there is universal violation of integrability at one loop due to diagrams like this. So there are multi-particle production in D = 4 because string is non-critical. And so one can calculate leading particle production on the worldsheet. And actually one calculate not just 2 to 4, one can calculate all one loop amplitudes. And there is a simple generating functional for this one loop amplitudes due to Polchinski instrumenter. And well, this functional, the coefficient in front of this functional is given by this expression. And then in 4 dimensions, 26 minus 4 is equal to 22, which is kind of becomes very reminiscent of the coefficient which appears here. Now, as a cross check, some zeros or the sanity check, one can repeat these calculations as a present of adjoint quarks or squarks. Then we know how beta function coefficient shifts. So that's the formula. And then one can match the shift with the coefficient almost in the IR, namely what one says. One says when I have adjoint quarks and squarks, they translate into new degrees of freedom on the string worldsheet. We just insert that corresponding pattern inside my Wilson line operator. And if I neglect the mass, then repeating calculation on the worldsheet, I will get that the particle production coefficient shifts by the same amount. Well, it's semi-obvious for scalar quarks because scalar quarks from the worldsheet point of view correspond adding kind of one extra dimension. And well, it works out for fermions. One way to see it is because we know, say, for n equal 4 superior mills, this coefficient is 0 because the theory is conformal and it corresponds to critical theory on the worldsheet because it's a critical string theory. So, well, it could be that still it's a coincidence, but well, I strongly suspect it's not. But the kind of the project of the explanation which I have, I should say, I spent quite a bit of time trying to really pin this down, but I'm still not successful. But the project of the explanation is that somehow this leading particle production is similar to kind of what I was arguing in 3D. It's again some factorized long time process, which in Nambu-Goto language will be coming from some zigzag Unruh radiation. And because it's factorized, it somehow appears both in the UV and the IR. So it's the same thing here. So somehow semi-classical effect or Longe effect, which we see in the IR, it propagates all the way into the UV. And there it probably can be related to some gluon splitting amplitude, something like that, which the beta function coefficient appears there. But so far, it's a level of guesswork. So I don't know the answer. But also, actually, this suggests that it should be kind of bringing this closer to the topic of the conference. It suggests, if this logic is correct, it suggests that there should be positivity bound on this particle production coefficient on the worldsheet. Well, because then when it becomes negative, which would correspond to supercritical string, so that corresponds to having Landau pole in the UV. So well, here we see that actually this meeting between UV and IR in some sense happens in intermediate scales, because in doing what I did, not really the IR calculation, because I neglected the quark masses. So I did the calculation somewhere at the kind of this intermediate scale, at lambda QCD scale. So it's more delicate, the story here. And so to finish this talk, I think that kind of I started with these two alternatives, kind of going from UV to IR and from IR to UV. But I think really in the theory of gravity, it's probably more interesting. So I think kind of there is a picture like that, which better represents what happens with UV, and they're really formed to like convoluted together in some consistent structure, and both views are complementary to each other, and that's what gravity does. So let me stop here. Thank you.
Thanks, Sergei, for we have time for some questions.
May I ask?
Looks like Arkady. Yeah, go ahead.
No, I wonder, Sergei. You know, in your philosophy, let's say that you're considering this as matrix and discussing this in terms of this resonances. Could it? But then I wonder whether black holes would show up in this scenario, and whether they would show up as a resonances, and if they show up as a resonances, on which sheet they would be. I understand that it's not a clear question, but I mean, I still wonder.
No, I think it's a very good question. Actually, that's for me. That's one of the motivations to think about this whole setup. So first of all, I should say that this time delay proportional to the energy, that's what naively one expects for Hawking evaporation time in 2 dimensions. If you just take Hawking operation time in different number of dimensions and goes through, down to 2. That's what you expect. Well, of course, in integrable model, it's hard to talk about black holes because there is no particle production. So I think actually, but I think that this zigzag, that's what corresponds to a black hole. So when you form this zigzag, there is a kind of some pocket of space formed during the collision. And if there is also, as I tried to argue, there is also one expects copious particle production. There are UV IR modes here. So I think understanding and really understanding confining strings with massless gluons present, which the physical case is very much relevant for black hole physics. Now, as for resonances, I don't think it's correct to think about black holes as resonances. And actually, this picture illustrates very nicely what's going on. So usually, when we like to associate long time delays to the presence of almost like presence of resonances, presence of metastable particles. But here we see that's a very different mechanism of producing long time delay. So here there is in this picture, and there is nowhere one finds anything like long lived particles. Instead, the resonance like the long time delay arises as a consequence of this creation of this region of space, and just kind of as a result, particles propagate over long distance, but there are no resonances here. So I think
right. But having in mind that black holes decay, right, evaporate, then they are resonances in certain sense, right?
Well, they're not resonances in sense there are no poles or zeros in the S matrix, nowhere anywhere close to.
No, it's that's what I'm asking about, right? But then it means
there is in the sense there is a long time delay. But what I'm trying to argue here, there are different ways. At least there are kind of one shows that in 2 dimensions there are two different ways to get a long time delay. One if there is a very long-lived resonance, and another if kind of there is S matrix has this unusual analytical structure which geometrically corresponds to creating a large region of space as a result of collision, and then particles just need to propagate over that large region of space before they escape. And that's, I think, much closer to what black holes are rather than actual resonances.
Thank you.